We're going to be doing a joint presentation today that includes folks from MIDAS and also me, and we're going to be talking about a specific project. The project that we're talking about is, well, I'm wondering if I should wait a second. I've got about 2 minutes till.
Yeah, we can actually just do a mic check right now, Don. If people can hear us, can you please through the GoToMeeting interface press the hand button or leave a comment in the question box? Yeah, I see some hands popping up. So I think we're good on the audio. We can get a few minutes for people to sign in. We actually had a lot of people registered. So
okay.
We can give it a few minutes, Don. There's no rush.
All right.
So also as an announcement before Don goes ahead and gets started, as he mentioned, this is going to be a joint presentation. Don is going to go through the Amec part of the project, and at the conclusion of his presentation, we'll actually leave it open for questions. People, you can type in your questions through the GoToMeeting software or interface, and we'll answer those for a few minutes or for whatever time we need. And then we'll go ahead and conclude the presentation with my half on how this can be done through MIDAS. So we'll have like a bit of a break for questions in between, just as an FYI. You can type in your questions as you're coming, everything you're seeing.
All right, I've got straight up on the hour, so let's go ahead and get started. So as I was saying before, this is a joint presentation between Amec and MIDAS. We're actually looking at a project that is still ongoing, as a matter of fact. So the project, this is an independent external peer review that Amec is in the process of conducting for both the Missouri Department of Transportation and for the Corps of Engineers out of the St. Louis district. So before I get into the project, I wanted to talk a little bit about why are we doing this series of webinars with MIDAS, and why are we hosting seminars that MIDAS can make these presentations. So I thought I would take a few minutes and just kind of give you a feel for some of the changes that are taking place in the geotechnical practice. And the biggest change is that we're changing the way that we own and use software. The historical model is what I call local procurement or local ownership. I thought about a couple of different other ways of talking about it: laissez-faire, software ownership, crony capitalism, whatever you want to call it. But the previous model is that every individual office was responsible for all the specialty software that individual office used. So, for example, if you used Slide, for example, well, the local office had to buy the Slide software, and then they had to maintain it, and it wasn't available for use by anybody else. It was strictly for that office, because typically you had to use a hardware lock or a dongle or something like that. So it had to be something that you could physically hand to somebody. When we did use software, we had to put it in a FedEx package, overnight it to somewhere, and that's just not real efficient. The new model is that our software, wherever possible, is going to be purchased by the company on a network basis, where we open up access to all of our practitioners. Now, this will do several things for us. Number one is that it will cut down on our costs, because if you own a copy of Slide or SlopeW or LPile or whatever, if you're not using that 8 hours a day, that's a waste of money. So we're going to be able to cut down on our cost of owning and operating software. We're also going to be more and more getting on the same page. I meant to a copy of this from our website, but one of the things that AMEC is selling is the ability to do world-class engineering all over the world at any office, and it looked seamless. So if you get products from Canada, you'll get a similar level of expertise and product deliverable as you would if it came out of Britain or the central U.S. or wherever. So that's kind of the reasoning why we're moving to this route. We're going to be moving more toward network software. We're going to be more moving toward company ownership so that the local office doesn't have to absorb those costs, which directly affect your profit contribution. The way we're going to do it now, it won't affect the local office profit contribution. It'll hit the company at the EBIT level, but not local PC. So that's going to be really, really important. The other thing is that we want to make sure that we're able to keep up with changing technology and sophistication in software. So there are lots of finite element programs out there. Most of them are 2D, as I've got on the slide here. But to be a world-class engineering firm, you've got to have 3D capability. Now, not every problem requires 3D analysis, but the ones that do, you've got to be able to provide those. Historically in AMEC, in Western Canada and the Western U.S., we've got several FLAC users that are highly experienced. FLAC is not network capable. It's a finite difference program. It's not finite element. FLAC has some advantages in certain situations, especially over large strain cases. But the interface in FLAC is my understanding, I haven't used it, but it's fairly difficult to learn. And it takes a lot of time and effort to become a solid FLAC practitioner. Up until recently, the other software that we've been using for finite element, not including Sigma, from GeoSlope, is Plaxis. Plaxis is, for a long time, been the standard finite element for geotechnical analysis software package. Some of the problems that we've had with Plaxis, though, is that it's very modular. You have to get all the pieces and parts and buy those pieces and parts and put them together to do various kind of analyses. So you would buy a regular 2D package, and then you would need to get a dynamics package if you wanted to do earthquake or other type of analyses that involves vibration. If you wanted to do seepage, you had to buy another Plaxis package. And the same thing was true of the 3D. So these things, while they work together, they are all in separate packages, and it's really expensive. The retail cost for Plaxis 3D is about $37,000. The retail cost for Plaxis 2D is $18,000. You put those together in one license that gives you both 2D and 3D capabilities, you're talking $50,000+ retail. Now that's a lot of money. In AMEC, we've got currently 15 current licenses of Plaxis. They're all hardware locked. We can't use them on a network. It's not practical to use them on a virtual machine. So we haven't changed. We haven't upgraded any of our Plaxis licenses. The oldest one's is 2003, so it's 13 years old that we haven't gone through an upgrade. And it's primarily the cost. So MIDAS, on the other hand, has a lot of advantages over Plaxis. Number one, it's less expensive. Number one, it's self-contained. You don't have to purchase a bunch of additional modules to make it all work. One license has both 2D and 3D capabilities. The drawing capabilities are just orders of magnitude better, and the graphical output is a lot better too. So MIDAS is, in my opinion, a much better software package than Plaxis is, and so we made the decision that we were going to phase out our Plaxis use and phase MIDAS in, and we did that a couple of years ago. Here in Nashville, we actually bought a copy of MIDAS, paid for it locally, amortized it, paid for the maintenance upgrade locally, and then we actually locally paid for the upgrading of our single dongle software seat, license seat, to a network version, And then we actually bought two additional copies. So the company owns 3 copies of MIDAS. They're all network licensed, and we're making that available to our practitioners. The other reason why I think finite element is going to become more and more important is that because the expense is coming down, our computing power is going up. I just see a lot more finite element analyses in the future, especially in the slope stability arena. So you can do, I think you can do more accurate analyses in slope stability, especially where you have flowing water, stress changes and stress distributions, and you can come up with, you can determine a factor safety in finite elements as you can in using a limit equilibrium, but you have a much more refined analysis. So the philosophy for GeoStudio, for example, is that if you have flowing water, you have to do a seep analysis, and then you do a sigma analysis, and then you take those the pore pressures and the stresses, and then you import those in the slope, and then it runs a limit equilibrium analysis where it goes through all these searches to come up with the individual trial surfaces. This is doable, but it's kind of cumbersome. And I just don't see that being the wave of the future when you can do all those steps in MIDAS in one package and in one analysis. So like I said, we currently have 3 MIDAS networks, MIDAS licenses. We are going to be steadily increasing the number of licenses. I'm not sure exactly how fast. The rate at which we increase our number of licenses will depend upon usage. When we have periods where we've got more people wanting to use the licenses than we have licenses, we'll buy some more. The upshot of this is that at some point we're hoping to get into an enterprise licensing situation with MIDAS, similar to some of the enterprise licensing schemes that we have primarily with Bentley and with Autodesk. So we're, in those situations, we don't actually buy the software, we're basically leasing it. We use it on a daily basis. When you want a license, you open up the software, it goes out into the network, and if a license is available, you tag that license and you start using the software. If a license is not available, it goes to a Bentley server, for example, pulls a license down and lets you seamlessly start using it. So we're hoping to get that way with a lot of other different software. So that's kind of the background of why we're doing these MIDAS tutorials, these webinars, is that this is the direction that we want to go, and we're going to be steadily working on ways to get there. All right, so let's move into the current project that we're going to be talking about today. So this is a independent external peer review that the St. Louis office is doing on behalf of the Missouri DOT, ultimately to satisfy the Corps of Engineers. This is I-55 in St. Louis. It's a bridge over the Mississippi River. You can see barely that there is a flood wall right here along the Leonore Sullivan Boulevard that ties into the abutment. They're widening the bridge to the south, and so they're taking out the flood wall, and they've got to recreate it, put it back. So the Corps wanted an independent review done on that flood wall. Here's a picture of the flood wall. You can see the bridge pier. This is bridge pier number 1. It's a massive concrete structure. It's hollow inside. There's actually some windows and doors there, so you can get inside. But they're going to be moving to the south. They're going to cut out about 20 feet of this existing flood wall, and then they're going to be replacing it. It's hard to see in this particular photo, but right about there is a seam, and the angle of the flood wall changes as you move to the south. I'll show that in some drawings here in a little bit. Here's another picture of that same area. You can see the doors, and there's some windows there that are below flood stage, obviously. But again, they're going to take out this portion of the wall, recreate it, as they move to the south. Another close-up shot showing the joint between what's called the stud wall and the flood wall. Here is an old drawing that shows the layout of the pier and the flood wall. So I'm looking at it, I'm standing on the back side, on the dry side, looking towards the river. So the river is to the top of the page, the land side is to the bottom. So the area that we're interested in is on the right-hand side. So the stud wall comes out, you can barely make these numbers out, but the stud wall comes out at 9 degrees. And then the angle changes, and so the angle between the stud wall and the flood wall is about 64 degrees. So it goes off at an angle, and so part of the flood wall is going to be perpendicular to the pier, and the other half goes off at a skew. Here's an old drawing that shows the flood wall, the cross-section of the flood wall shows all the reinforcing. You can see that the geometry of the base of the flood wall is a little bit different. It goes down at an angle. There is a shear key here at the front. There's a flood cutoff wall right here. There's another one back here in the middle. And then you have an existing vertical pile, and you have 2 battered piles on the back. Here is a picture, an old drawing of the base. So you can see how on the left-hand side this is all perpendicular to the pier, and then once you come out a certain distance, then you start going off at a skew. This is a drawing put together by the consultant for the new flood wall. They are leaving an existing 18-inch pile. The nomenclature here is UIP, which stands for use in place. So they're going to demo the old flood wall. They're going to leave the existing pile in place. They're going to add a couple of battered piles in, and then that's going to be the new configuration of the wall. Here's a detail of the proposed piles. They're going to put an 18-foot rock socket in. This is a 20-inch OD steel pipe that's drilled into a depth of 18 feet below top of rock and socketed into the ground. And then here's a compression pile that's being drilled in 2.5 feet into the rock socket. So our job was to take the plans and specs and calcs and do a peer review. So this is a flow chart that the consultant, the geotechnical consultant, did for the bridge designer, doing a seepage analysis, trying to figure out what the lift was for the wall. Here is a boring log that shows what's underneath the wall. There was several borings taken along the alignment of the bridge. There was one boring taken over on the abutment side. It shows a silty clay with sand down to a depth of about 13.5 feet. And then it has a sandy silt down to a sand layer. Then they've got fairly hard competent limestone at about 40.5 feet. So I pulled this out of the calc package that the bridge designer put together. You can see here where they're trying to figure out what the forces are on the flood wall. So they've got some active pressures, they got at-rest pressures. They finally figured out that the at-rest pressures would be equal and opposite, so they didn't worry about them so much in the analysis. So they put together a finite element model to try to figure out what the forces on the stem and the base were. And here is the nodes that they used in one cross section for their model. Here are the nodes that they put together for the base of the flood wall, and showing the layout of the piles, both the existing piles and the new piles. And then they put together an Excel spreadsheet to try to map those loads onto those individual nodes. So there are 67 pages of spreadsheets, printouts that look just like this in their calc package. Okay? Really difficult to make sense out of this given the way that it was put together. And I'm not saying this to criticize, because I mean this is, you know, you see this a lot. This is the way a lot of finite element problems are done, you know, nowadays with various software packages. So after doing all that, they put together some load cases. So they had a 500-year flood, a 100-year flood. They used service loads and they used factored loads to come up with their design cases. And then they made this this really important assumption. So the assumption that the designer made is that we're going to ignore the soil. We're going to assume that the soil's not there. We're going to treat the piles just like they're a structural frame for a steel building. We're going to assume that they're fixed in the ground. We've got a tension side and a compression side. And we think that this is a conservative analysis, because if the soil was there, then we would have lower bending moments in the piles. Okay? So that was the assumption that they made. So they took a bridge software structural package called LARSA. Amec actually owns this. We have a copy of LARSA in our bridge office in Denver. And it's a great software package for bridge engineering. Here's the model they created. So they built a model, and then they used the spreadsheet to go in and place pressures at individual nodes. And they ran the result, and they printed out 115 pages of output that looked like this, which, as you can imagine, is really, really difficult to make sense of. But finally, they boiled it down so that they had 5 piles, and they came up with these bending moments in those piles. So on pile number 1, the maximum bending moment was 14 kip feet. On pile 2, it was 31 kip feet. On pile 3, it was 33 kip feet. On pile 4, it was 34. And on pile 5, which is right here on the back, they came up with the maximum bending moment of 42 kip feet. So I'm looking at all this stuff, and I'm trying to figure out, is 42 kip feet reasonable for this analysis? And I had my doubts. Those seemed like they were kind of low to me. But how do I go back in and determine if they're low, or if they're high, or if they're reasonable, or what? Just based on my experience, they look kind of low. So here is the model of the wall that we actually have. All right. So I made a model of this in AutoCAD, and then I put it in 3D PDF, and it's going to pull up here in a second, hopefully. So here is the model that I put together that shows the actual geometry of the wall. So you can print these things, and the cool thing is that MIDAS, you're able to print these in MIDAS, these 3D PDFs that you can rotate and see what's going on. The other cool thing about these is that when you create them in a CAD package, you can create layers, as most of you know, and you can turn these on and off. So I can turn off the flood wall, I can turn off any particular pile, I can put them back on. So you can really see what's going on. So this is the model of the wall that's proposed. I couldn't create that in any of the software that we had. So I looked at doing this in Group. Group is a finite difference program that uses PY curves to come up with the bending moments and the actual capacity of a pile. Pull this up. So this was the best I was able to do in Group, was come up with something that looked like this. So I modeled this in Group. Turn the base off here. So I modeled this in Group, and I came up with loads that were higher than what the Larsa came up with. So the loads that I came up in group were on the order of, instead of being 40 kips, were on the order of 60 to 80 kip feet. Okay, so that's when we, and I did this just to show the difference between what we can do in Larsa, what we can do in group, and then what we can do in doing a MIDAS analysis. All right, so that's pretty much the end of my presentation. I think I got one more slide. Yeah, so here's a picture of how group processes that data. All right, so let me turn this over. I guess I do change presenter, right?
Hi, Don. Actually, do you mind for, we can maybe leave it for a few minutes, couple minutes. If anybody has any questions, they can type it into the question box on the half of the presentation you just shown.
Okay.
I don't really see any yet. We'll give it a minute or two just in case there's people who are typing it in.
I'm sure there aren't any questions because I did such a good job of explaining that.
That might be a reason why also there's, they want to know more. It seems people are okay. We'll have another chance at the end of the presentation of my half for questions again, and it can be about either my part or Don's part as well. So for now, just to continue with the flow, then I'll go ahead and change to my half.
Okay.
But thank you, Don. That was very interesting. And so we'll do. You should be able to see my blue slide.
Yep, I can see it.
Great. Okay. And for a second, Don, I'm gonna just mute your mic so there's no positive feedback on the audio. So welcome everybody to this presentation. My name is Francisco Martinez. I'll be showing the, I guess, counterpart of what can be done with MIDAS. I'll start directly by showing the 3D case for this retaining wall project that Don was mentioning, but then I'll push it a little bit further and show you some of the unique features that MIDAS has as far as interaction with other structural softwares. So we'll look at a case for building substructure interaction. We'll look at a case for a bridge consolidation analysis, and lastly, a tunnel excavation that affects an adjacent structure. And these were all questions that we got as feedback from our last session, so we thought it would be good to cover some of this in this session as well. So just a quick recap of everything the program can do, and I'll show you directly some of these features in some examples. GTS NX is actually a all-in-one software. Not only can it do 2D or 3D in the same platform, but here's a screenshot of the types of analysis it can run. So most common, some quick things can be the static analyses, but what really pushes the boundary are some of these advanced construction stage analyses that are allowed to be considered semi-coupled, where you can actually change between types of analyses like stress and seepage or slope all in the same model, all in the same sequence. But then you can also do some other pure analyses like consolidation, slope stability by different methods in 2D or 3D. The dynamic abilities were actually some of the questions that we're getting, and we'll show some of that, but we can do all kinds of seismic analysis as well as moving load analysis. And lastly, the seepage, where we can do steady state or transient. So let's go ahead and get back to the original question, or the case study we're doing for the 3D float wall. So GTS NX, one of the biggest advantages it has is the compatibility with all the AutoCAD programs, how easy it is to import these files. So Don sent me his AutoCAD file of the flood wall. He gave me a little bit of the background of more or less what he was trying to study, the results, primarily structural, that he was concerned about. And so from that, I was able to just simply import the lines, this AutoCAD file lines, and do a few AutoCAD commands like create faces on some of these and then extrude them to make solids, to then finally have the mesh. Here is isolating just the wall and the piles. And here's the ground. Now these are not according to the actual project. We messed a little bit with the geometry and distribution just to show you that in a 3D case, you wouldn't necessarily look at a straight horizontal wall. You might actually be interested in some of these uneven distributions. So we gave it a bit of a bulge, and a little bit further we'll show other terrains that we were able to analyze. But then just keep in mind that the the water would be on this side. We actually did a construction stage analysis. We varied the water level, as Don was mentioning. They cared about the 100 years, 500-year floods. So we actually increased the water level, and we can see how this pore stress affects or redistributes the moments in the piles. So here are some of the quick results that we can see for the ground itself. If we're going through these semi-coupled analyses, you can actually first obtain your pore pressures in one stage, and then subsequently see some of the stresses or displacements directly on this stress stage, as we call it. So we're looking at the nodal head. As I mentioned, the water's on the right side. We see here the pore pressure, and we see some of the displacements on the wall itself based on this pressure. And we see here is actually the water level as it's seeping through the wall or under the wall to the left, and we see two different colors to show the different, I guess, final stages of the water through the stages that we went through. So we actually increased it by a few feet, and this is kind of reflected here as it's seeping through the left. More importantly, however, as Don had mentioned, is the structural results on the wall itself and the piles. So the program allows you to have stresses, moments, forces directly on 3D surfaces. 3D elements don't necessarily always show these, but GTS NX has an additional kind of element to extract results like this. So we can apply this to the surface of our wall and get the moments, get the forces directly distributed over this. And as we would expect, the bulge is going to have a higher concentration. But more importantly, looking at the piles, we see here we have our axial forces, our shear forces. But as Don was making an emphasis on the moments, we're looking at a moment of around 140 kips feet. So going through the transition, the original estimate was around 40, which is a vast underestimation. We're looking closer to almost 3 to 4 times higher in our final model. And this gives you the advantage of actually being able to see the distribution. So I'll actually bring in the model itself. So what we can see here actually is also looking at the moments. We see this distribution, and we're looking here at 120 kips feet for one of the stages, as I mentioned, where the water level might be at a certain height. And then further on, as we see here, we have further construction stages. If I go then to the final stage, after I have updated my pore pressure to a higher level, we see now that it actually increases. So the program does allow you to easily go through these manipulations, these definitions of stages in a very easy manner between kinds of analysis. In this case, as I mentioned, this is a semi-coupled seepage stress. We can also make it even a slope stability if we had a different kind of soil or distribution of the geometry like we see here. So in this case, we actually additionally added some other kinds of elements, shell elements on the wall. We varied the terrain. And what we want to emphasize here is that in a lot of these geotech programs, there's going to be, if you're interested in an interaction with some other existing structure or some other case, you usually model, let's say, a bridge pier as a point load or as a pressure load. So the structural engineers give you what they're obtaining as their pressures. This geotech engineer comes in, puts it as a load, gets his results, and then he can send back some information to the structural engineer about the stiffness, the K values. If they're lucky, the structural engineers can model the foundation of the structure within the same program, but they have to model it as soil springs. So this is a current method for a lot of softwares. What we want to show you is how we can actually take this a bit further, and this is actually unique to MIDAS. So we not only have a geotech software, but we actually carry the full line of civil engineering. We have a bridge software called MIDAS Civil. We have a building software called MIDAS Gen, and these actually they communicate. We can actually import the full structure into our geotech software with the properties, with the loads, and allow you to then model the ground and structure in a single file and run it together. So let's take a quick look at what that could look like for some of the structural engineers that might be present or within some of the Amec offices or clients for that matter. So if we have a building, this is our MIDAS Gen, and this is the building with the ground imported for the geotech and GTS NX. What we like to do in this case is a seismic analysis, a soil structure interaction comparison. So luckily, Gen actually is a pretty advanced tool in itself, and you can model the ground as soil springs. You can apply these boundary conditions directly to the foundation and to your piles. And so we want to, if we're interested, we would like to see how under the same seismic load and in this case for both of them you can just copy paste from Excel your own table, what the results would look like, what the differences would be between the methods. So in this case, we import the structure, we model the ground. GTS NX allows you to have what are called free field boundary conditions, so that there's no concern about the wave bouncing around in the underground and your results being overestimated. We have advanced boundary conditions for these kind of seismic analyses. So then if we take a look at the results, and I'll open the models in a second, purely looking at the piles themselves, here comparing the forces, the actual forces in the moments between our structural software with the soil springs and our geotech software with the ground model as 3D elements. For the send seismic load, we see that we're underestimating the structural software with its soil springs has limitations and underestimates by almost 30% of what we're looking at forces and moments in itself. So that's significant. It's enough if we're looking at the foundation. If we were to look at the whole structure, which is also of interest, we see that some of the other major displacements or axial forces are not that off. But if we look specifically at the moments themselves, they are redistributed, and there is again an underestimation for these. So for seismic analyses, and we'll see other cases in a little bit, it's actually a significant underestimation. So we're looking here at our structural software. Just kind of give you a preview. It's a similar interface of commands based on icons. And again, we can do all kinds of construction stage analysis or seismic analysis, different kinds of loads distribution within the structural software. But for the geotech, Amec being the main focus, what you would really like to be able to do is something where you take it to a closer approximation of what's happening, have that nonlinear condition, those nonlinear properties of the soil themselves. And if you give me a second, I can actually show you that GTS NX also has very advanced constitutive models for these kind of seismic analyses, including liquefaction. And so you would be able to model a softer soil beyond what a nonlinear or a linear spring would be able to model in any structural software. So you would see here these advanced numerical theories that allow you to model the ground nonlinear properties in a much more realistic way or advanced way, but with the structure in place. Moving on to another case, this would be for the interaction with our bridge software. So this is a bridge from our MIDAS Civil, similar to Larsa, but we'll see that it's actually, or from what I hear, much better reviews as well. And similar interface to what we saw for the Gen, where we have the icon-based commands. We're looking at some of the results for displacements under the load. In this case, we haven't modeled the substructure. We actually just fixed the base, the tip of the piers, and the end of the bridges. So we see kind of an uneven distribution along like the longer segments of the bridge as far as like the load affecting the displacement. But what if you really have a soft soil in your problem? What if there's some sort of drainage condition that you have to consider? So GTS NX would allow you to import the structure, model the foundation with the piles, and then have this advanced constitutive models for these soft clays with these drainage conditions, and as well as model the construction stages. So what you would be able to see then is a settlement over time, not just immediately based on a static load. So we're seeing here the construction process itself, of the installation of the foundations, the bridge itself, and then a long-term, maybe 1 year short-term, but you can actually make this as long as you want. So we're looking here at settlement over a 1 year period, and we're getting closer to 6 centimeters. Originally, we were looking for a static fix of closer to 2, and it was only, I think, based on the longer segments of the bridge. But here we're seeing a better approximation of what actually be happening over long-term. And then if we look, as we're saying, the displacements, also the forces we would expect to be distributed differently. That we can see as well here the forces for the piles, not just the piers themselves. And so we see almost an underestimation by half if we were just to fix the base for the same static loads. Same for the moments. Here we're just actually looking, it looks a little bit inverse. It just has to do with the orientation of the elements themselves. We can actually reverse this in either program and we would have the same kind of distribution. But again, the range of values is also by a third underestimated for the moments. And lastly, the shear forces. We're actually looking at much more than a third, close to 5 times underestimated. So when you start to consider how a bridge is going to settle, how these forces and moments are going to redistribute, it becomes really clear that fixing a base, which is still done by a lot of programs that lack the ability to do even the soil springs, it can be a big miscalculation. And lastly, I like to show, there were some questions about what if there's some new or existing structure and there's going to be a new project taking place, and we like to see how these effects are going to affect it. So consider the same bridge, the same model, but now we're actually going to dig a tunnel going under it. So we are located in Manhattan. It's be very similar to something happening like with the Queensboro Bridge. There's an existing bridge, and there's also a subway line that goes very close or directly under it over to Queens. So if this was to be the case for a new bridge or a new tunnel under a bridge around the city, this would be the kind of analysis where they'd be interested in seeing how this new excavation is going to affect the settlement of this existing structure. So we're seeing here now, the structure itself, we're clearing the displacements because we're only interested in seeing how the new excavation is affecting. So we see as we're progressing with the excavation, we actually start to see a few centimeters of settlement. It might not be significant, but depending on some of the conditions, size of tunnels, this could become an issue also with the redistribution of the actual forces and moments. So some of these might look the same distribution, but actually, if you recall, the moments themselves actually look a little bit different and they're much higher now. So the shaking up of, even if it's a few centimeters at the foundation, it's actually redistributing, maybe misaligning a little bit the bridge, and this can become a concern. So all these, we're also seeing here some of the forces on the tunnel itself and on the support elements for the tunnel. So all these kinds of advanced analyses you can do all in the same model. This would actually be a pretty complicated case to go between different softwares, different offices. We can do it all in one. So in conclusion, I'd just like to give you a quick recap of just a screenshot of what we've been looking at. We looked at some of these capabilities, but the program can do anything in terrain-wise, geometry-wise, analysis-wise, anything that needs to be done for geotech. So given that compatibility with the AutoCAD files, we can actually probably the best software for capturing irregular geometries, especially in 3D. As we have shown in the previous sessions and we're looking at now, the program can do axisymmetric, 1D free field being one of the seismic capabilities, 2D and 3D all on the same platform. It's an all-in-one tool. As we saw, we can do all the analyses that you would need, including the direct method for substructure interaction, bring in the structure. We saw that the substructure method actually, it might be sufficient, but once you have a comparison method, a calibration method, you can see that it's actually, especially for nonlinear behavior like in an earthquake, underestimates the results. And so with GTS NX, you can actually have this full structure interaction importing directly from our building or bridge software, and it would allow you to get more accurate results. Given that you're modeling the ground in 3D for seismic analysis, you would actually also need to first calibrate it, which can also be done internally by all other methods within the program, like 1D free field and 2D linear equivalent, so that you can have this nonlinear behavior of the ground free field first and then have the structure in place. But that would be the conclusion of our session. You can email me any of your questions. I'll leave the session open. You can type in your questions into the box. If you like to see or find more information about the program, we actually have tutorials in this page as well, or you can just directly email us. But I'll leave the session open. I'll open the mic up again for Don. And so if you have questions at the moment, you can type them into our question box. But that would be the conclusion of the presentation. Thank you for your time.
Okay, great. That was very exciting stuff. The other thing that I wanted to mention is that not only do you have, and Francisco brought this up, but not only do you have the capability to do earthquake loading, but you can do train vibrations, you can do blasting, you can figure out how much structural damage you might have from pile driving. There's just lots of things you can do with MIDAS that are just really cutting edge.
The question, does the software have unsaturated soil mechanics modeling capabilities? So I'll go ahead and open a model to show this. The short answer is yes. when you're defining the material properties, you could actually choose, some of these advanced, soft soil constitutive models, but even the not so advanced nonlinear constitutive models, there's a tab for porosity where you can actually define conditions for the unsaturated or undrained soil properties, permeability coefficients and such. So it's also used a lot for some of these dam seepage analyses that require a careful definition of these conditions of the soil. While I have this model open, I actually just wanted to, this is the same model that I did for the consolidation of the bridge as well as the excavation of the tunnel. What I'll just show quickly is how easy it was to define both of these construction stages, even though they're different kinds. So we can see in the program, in the workstream, we have two sets of construction stages. We see here the kinds of construction stage analysis you can do. So we have the stress, the pure seepage, the semi-coupled, fully coupled, the consolidation, and actually the stress and seismic analysis. So for the consolidation analysis, I was able to obtain these results. As I had shown in the previous webinar, this is how we can define construction stage analysis, and we have here a clear view of what's happening at each stage. So it's easy to define them by dragging and dropping into the activate window, define a time step, like a duration for consolidation analysis. So here we're activating the foundations. If I go to the next stage, we're activating the bridge, and then the loads. So this would be as well over a 1-year period. We define it here, well, it's in seconds, but you would define it by days. That would make it more sensible. And then similarly for the tunnel excavation, we would then have the initial stage be the bridge already in place, and then what we would start to do then is excavate. We can start seeing here now that these sets are disappearing. So by dragging and dropping from our sets, we can start modeling excavation processes as well as activating different loads. So just to give you an idea of by drag and dropping, we can define, even within the same model, different kinds of analyses and group the results in a very easy to manage window in the workstream. So for instance, here looking just at displacements at different stages, I can navigate them with this bar at the bottom. I can actually make cuts, plane cuts, and see how this is being affected over the whole process of the construction. And by the same token, I'll just show the same for what would be the tunnel model. So we're seeing here as the excavation progresses, it's being excavated from both directions, a redistribution of displacements and forces. There doesn't seem to be. Are there any other questions? We have a few minutes. We can provide. If people need to type them in, or as I mentioned, we can directly answer you by email.
The other thing we're going to do is that the software is very powerful. It can do very complex models. There is a learning curve to be able to use the software effectively. So we're going to be continuing to put out tutorials. MIDAS has a lot of tutorials. They recently switched over from GTS to NX. I think that was, what, 1.5 years ago, Francisco, something like that?
Closer to, I think almost 3 years now.
Almost 3 years? Okay. So a lot of the...
2 years.
Okay. So the interface is a little bit different, and some of the tutorials that they have from GTS days haven't been updated yet. So we're going to be developing some more tutorials in-house that are going to start out very simple and kind of build on the capabilities of software as we continue to use it. We've made a commitment to MIDAS. They've made a commitment to us. They're going to be one of our primary software partners moving forward. So we want to continue to be able to develop our capability to use this software to its full power.
Don, there doesn't seem to be any more questions, so this can be like the concluding part of the session. But
Okay.
they can directly email us, get in touch with us, or with me directly to the email that I'm showing on the screen, which is the same one that people had sent their questions previously. And so with that, you can visit our page as well. You can get a little bit more information or download some tutorials. But thank you everybody for your time. Thank you, Don, so much for your contribution for your part of the presentation. And
if you want a PD8 certificate, just send me an email. Let me know, and I'll send you out one.
Great. So we recorded the session, and we'll be sharing the material with everybody by email.
All right, sounds great. Thank you, folks.
Thank you, Don.